So what is BLUPF90? It's a collection of software to do computation in A, B, and G. A, B, and G means animal breeding and genetics, and actually means animal breeding, yes, and quantitative genetics. So that it started with programs that were written in 1997-8 by Ignacy Mistal. Ignacy Mistal has been writing software for genetic evaluations and remol since 85 or something like that. And he was teaching his regular course for mixed models, and he realized that he didn't have like a good explanation on how to program. So from scratch, basically, he wrote a simple program, and then he extended, and then he extended it again, and now it's a monster. And it's written in Fortran, modern Fortran, Fortran 90. If you talk to people about Fortran, they are horrified because Fortran started in 1954, I think, and it was impossible to read. Modern Fortran is much more kind of friendly. But, and over the years, there's been a lot of people involved, and it's kind of simple, efficient, and it's very comprehensive, and it uses very general models. And so the main contributors is Ignacy Mistal, who created, and Sogo Tsuruta, who has been working with Ignacy Mistal since 2000, more or less. I was a postdoc of Ignacy. Ignacio Aguilar, who works in INIA, Uruguay, was a PhD student. Yutaka Masuda was a postdoc, and Matthias Berman is now a postdoc. He was a PhD student, and so Matthias Berman was the student of Carolina, who was the postdoc of me, and I was the postdoc of Ignacy Mistal. And there's a few more contributors, and one of the things that we try to do is to convert research into code. So when we have some idea that we think it's reasonably useful for people, and instead of just writing a small prototype, we try to put it into BLUPF90 so that eventually it can get used by more people. And we call it a software because there's a bunch of programs, but lately we decided just to stop maintaining some programs because it was just too complicated to keep track of all of them. So we now, basically, the programs that you mostly use, I guess, is BLUPF90 Plus and Gibbs F90 Plus. And BLUPF90 Plus is a mixture of the old BLUP and Remor programs, and Gibbs F90, that's basically an estimation of variance components. So these are these two, right? And then there is another kind of software that we are not really interested today. So this thing here is just programs that are used for very, very large genetic evaluation. So in using the public version of BLUPF90 Plus, you can probably run 1 or 2 million animals with no problem, and up to, I think it's 25 or 27,000 genotyped individuals. These things have no limit. The only limit is the memory that you have in your computer. These programs are different programs. They are to process SNP data, quality control, solving SNP effects and stuff like that. But the one that you are going to use today is this BLUPF90 Plus. And there is an extra program which is called RenamF90, and it's basically you have your data file created by Excel or using R or whatever. It's just a text file with animals, records, temperatures, health, whatever, and it will convert into formats that are readable by BLUPF90 Plus. But you are not going to use this today because it's already, everything has been prepared. So BLUPF90 Plus does two things. One is the mixed model equation. So you remember the equations that I showed you? So you tell BLUPF90, okay, this is the model, this is my record file, and it will create the mixed model equations, it will solve the mixed model equations, and it will yield solutions. That's one of the things it does. The other one is variance component estimation, so to estimate these genetic variances and heritabilities and correlations. And this is how you use BLUPF90 to estimate. You just tell the program, instead of running the default BLUP or mixed model solver, you do Remor. And the interesting thing of BLUPF90 Plus is that because it was written in a manner that is kind of easy to extend, over the years we added lots of extensions. So from the beginning it runs animal models, maternal effects, and random regression, and this is permanent environment. This is maternal permanent environment for people that work with, for instance, growth. Growth is usually considered to be early growth is affected by the individual, but also by the mother of individual in ruminants because the mother gives the milk. And it also, from the beginning, does random regression, and then you can cheat to make a social interaction models. So basically, this is in a pen, you have pigs, and one pig is disturbing the other one, and you can model that some pigs are worse than other pigs. And also, you can run multiple traits. So it's kind of very comprehensive. And this is the general introduction. Now I will, so in principle, later you are going to use this BLUPF90 plus in your computers. The parameter files have been prepared, but I want to walk you through these parameter files and the data files and how we prepare things, because it sounds very cryptic. That's what we said before. It's not obvious how to do things. So this is the same example, right? We have the records. So we have records, we have temperatures, we have cities, and we have animals. So we need to tell this to, and we have these variances and covariances. So the first thing that we need is a data file. So I wrote this in my computer. It's a Mac, so it has kind of Unix inside. So I wrote this records file. It's not very difficult because it has just 4 lines. But you see that we have the milk yield, the number of the animal. It's sorted, but it doesn't need to be sorted because I just wrote it that way. The city, but here we don't have Paris and Cordoba. Here we have 1 and 2. 1 means Paris, 2 means Cordoba. And then we have the temperature. And then we have something that is called, so BLUPF90, I didn't put it here, but BLUPF90, you say, BLUPF90, you read a parameter file. And a parameter, in R, for instance, in R, you say, okay, you run me a linear model with this kind of equation and this data frame. Here, you don't open a session in BLUPF90 and talk to BLUPF90. You just say, BLUPF90, do this. And this is a parameter file. So this is the parameter file for this model. So the parameter file was one of the things written by Ignacy in 1997 or so, and it's basically numbers, and it's kind of very cryptic because usually here what you want to have is here you have something like, I don't know, milk yield, city, temperature, animal, whatever. You want to have names, but here you don't have names, you have numbers. So on one hand, that makes things complicated, but on the other hand, it makes that you can do things that you could not do with names. So the first thing that we have is that it says, okay, data file, this is the actual name of the file. So this is the file records. Then you say we have one trait, we have 4 effects, we'll go into that later, and we have one, and we say we have one trait, but the observation is in column 1. So that says where the trait is located. That name is not very, it's a bit kind of ambiguous, but anyway. So it says, okay, this is, the one trait is in the column number 1, which is this column. We are good with it. And then there's something called weight, and the weight is not the weight of the animal, it's not 3 kilograms or whatever, it's the statistical weight. So if you don't put anything, you just leave a blank line, all observations have the same weight. But you can say, oh, you put an extra column and you say this observation is 2 times more important than this other one. So you put 2 and 1, and that happens if you work with means. For instance, you just took an animal and you took means over a period and you just get averages of that, you can put that kind of weight. Then we have a second part where we define the linear model. So this is how you write the linear model when you want to do algebra. This is how you want to write your linear model. So our linear model has 1, 2, 3, 4 components. 4. The effect of the city, the effect of the temperature, the baseline of the animal, and the slope of the animal. So we say here, number of effects, 4. Our model has 4 effects. So here, under this headline effects, we need to prepare 4 lines. And the way it happens actually, that's interesting to know, is that what the Fortran code is doing, the Fortran code reads this. Then he says, oh, now I'm going to read the next line. So the next line needs to be the name of a file. It stores the name of a file. Then it goes here, it reads this, it reads this, it reads this 4. When it arrives here, it says, I'm going to read 4 lines. 1, 2, 3, 4. If there are 3 lines, it will complain. If there are 5 lines, it will complain. It expects actually exactly 4 lines. So this is why this information and this information need to be coherent. And the fact that it's sequential is not like in other software that you read the whole thing and then you kind of parse. Here it's parsed sequentially. So what does this number mean? So we have 4 effects. So we say, OK, what is the first effect? So the first effect, we want it to be the series effect. So we say, OK, so actually, we want it to be the series effect. The series effect is stored in column 3. So we say this is in column 3. And then we need also to tell BLUPF90, because BLUPF90 is not going to read the whole data file and just deduce by itself there are just 2 series. You need to tell them there are 2 series. And you believe me, BLUPF90. And if you put there is 1 series, then it will be a problem. So you need to say there are 2 levels. And the third thing that you need to say is that it's a cross-classified effect. So sometimes it's also called a dummy effect. So if you read a book on ANOVA and then you go to ANCOVA, people, depending on the statistical field, people start with regression with covariates. But in other places, they start with regression with effects. Actually, you can put both in the same framework if you realize that you have something that is called cross-classified effect and something that is called covariable effect. And the cross-classified effect is an effect of this kind. Either is Paris, and it's a 1 for the effect of Paris, or it's nothing else, and then you have a 0. This is another cross-classified effect. Either is 1 for this animal, or is 0 for all other animals. So the way it works is going to read this thing, and it's going to say, OK, this is the first series, put a 1 here. This is the first series, put a 1 here. This is the first series, put a 1 here. Oh, this is the second series, then I put a 1 here in this column. And this is how these matrices are created. Then you go to the second effect. So again, so this is number 4. But number 4 doesn't mean that this is the 4th effect. It means that it's the 4th column. Yes, it's in column 4. So you go here, and you actually get this thing here. You say, oh, this is the thing that I want to read. And then you say, it has 1 level, because here we have 1 level, right? We want to multiply this thing, but just this small number. It's just 1 scalar. So it has 1 level in the equations. There is 1 unknown. And then you say it's a covariate here. So instead of this game of putting 1s and 0s in places, it just fills with whatever is read here. Then you have the effect, the third effect, which is in column number 2, and it has 4 levels and it's cross-classified. So it will say, oh, this is the level number 1 here. So I put a 1 in the level number 1. This is level number 2. So I go to here 1, 2. Level number 2. I put a 1 and I put 0 everywhere else. 4. This is level number 4. So 1, 2, 3, 4. Level number 4. It will be the number that gets here. And then we have the tricky one.
Excuse me, address?
Yes.
Does it correspond to the number of animals you have? Or that level 4?
That level 4 is the number of the animal, yes. This is the 4th animal.
Yes, so you put according to the number of animals that you have.
What you do is you have a big pedigree. The pedigree may have more animals than what you actually have in records. So you number that 1, 2, 3, 4, 5. I mean, BLUPF90 does one order. It could be another order. The order is not important. And then you go to the data file. You say, oh, this is animal France 64001. And they say, oh, what was the integer number that I already assigned to this number? And you say, it's number 8, for instance. And you plug number 8. Is that answering your question? So it's the numerical ID of the animal that gave origin to this record. So if you say that so this is about coding and recoding, but so this is animal number 4 had this weight or this milk yield.
Okay, so my major question is on how to, for example, if the numerical ID I have up to 1,000, for example, and then under the second column where you explain the effects.
Here?
Yes.
So here you have 1,000.
Okay, yes.
Yeah, you have 1,000. And if you have these 4 animals, but then we had 6 more because they are just in the pedigree, here we will have 10. But that would be because it's an animal effect, actually. So, yes, the last one is the most sophisticated one. So here, it's a mixture of both covariate and cross-classified, actually. So we say, okay, it's in column number 4. Column number 4 is here. But then we say it has 4 levels. And say, come on, if this is a regression, we have a regression here. There is just one unknown, just one scalar. So how do you come that actually you have this vector of covariates, but here you have 4 levels? And actually what you want to do is you want to assign a regression coefficient for animal 1, a regression coefficient for animal 2, another one for animal 3, and another one for animal 4. So what you say is, okay, this is in column number 4. It has 4 levels. It is a covariate, so it's not 1 and 0. But then you say it's nested, or you need to assign this value to the position that is read in column 2. So the software is going to say, okay, I'm reading. He goes, first animal, it has a 58. 58, but I need to look at column 2 to get the position of the animal that is affected by this. So you go to column 2, it's animal 1. So you come here and it's, okay, I put in the column 1 here the number that is read here in position 58. Puff, and it assigns the value. Then for animal 3, it goes, it says, for record 3, it goes, this is 70, this has a value of 71, but I need to assign to the position in column 2. So it's a 71 to that position, which is 3, so it puts a 3 here. So in that manner, you have 2 things. You have an overall effect of the animal, because it's just multiplied by 1 always, and it doesn't matter what the temperature is. And then you have a value of each animal that goes multiplied by the temperature, and this is the non-reaction part. Okay? It's a bit tricky to understand at the beginning, because one gets very confused with all these numbers. But the way to think is to remember that if you want the norm reaction part, you need to tell the software what animal does the temperature refers to. So just to summarize this thing is effect number 1, 2, 3, 4. It's just the order of reading. The number that you put here is the column, is not the number of the phase. So people get confused because the software says effect number 2, and they look at the 2 here, but the effect number 2 is actually this one. And then you tell the number of levels, and then you tell if it's covariate or close classified, and if you need to do this thing of assigning covariates to specific animals, or you put a number here. Then we have the covariance structure. So this is a pedigree relationships and a covariance across traits. So for the residual variance, it's very easy. You just have this title, random residual values, and you just put the number too. This thing is a bit more complicated. And the way it works is also a bit strange, because you say, okay, I have 2 effects, baseline and slope, but I want these 2 effects to be correlated. So the way that you tell this in BLUPF90 language is that you call this a random group, and you put 3 and 4, and 3 and 4 refers to effects 3 and 4, not to columns 3 and 4. So in our case, it's the last 2 ones. And then you define. So this is how you define that they have to be combined in the covariance structure. And then you say, okay, this group of things that goes together is of a random effect type. It's called additive animal. So it's the regular animal breeding pedigree relationship matrix that and for that you need a pedigree file that in my case is called PET, and it's very simple. So it just says that animal 3 is doctor of animal 1 and animal 4 is doctor of animal 2. When it reads this thing, it will create this relationship matrix, pedigree relationships, and then the last thing is that you define the covariances of this thing and this thing. So that's the genetic parameter part. So you say, okay, if the genetic parameters are the variance of this thing is 30, the variance of this is 3, and the covariance between the two is -1, you just put these numbers here. So good. You have the slides, so if you need to reread again, and you will reread again, you have them. After running, you get solutions, and you get a file that is just called solutions. And the header of the file is trait effect level solutions. So trait, we just have one trait because, I mean, we have one physical trait, so it could be weight, but we have two genetic traits. In a way, we have, you could call them traits. You have this intercept and the slope. But actually, for us, these are two different effects, right? So you have the effect on the level. So the effect number 1 is the effect number 1 in the model that we said that it had two effects, and it's Paris and Cordoba. So we get two solutions. This is the solution for Paris, the estimate for Paris. This is the estimate for Cordoba. The effect number 2, there is just one solution, and it's the fixed regression at temperature. The effect number 3, we have 4 solutions because we have 4 animals. So this is the solution for the first animal, and this is the solution for the second animal. And the effect number 4 is the same. We have the solutions for the first, second, and third animal. So you go piece by piece reading, and you say, I want to extract my effect number 6. So you write a small program, you read everything, you say, just give me things with a 6 here, and then you do whatever you have to do. And there is an agreement because between the number of levels that you put here. So these two, you have 2 here. This is 1. You have just one solution here in effect number 2. Here you put 4. So there is 4 solutions here, and there is a 4 again, and you have 4 solutions here. So when the software reads this, it will prepare as many solutions as things you have here. Well, I'm done with this. You have any question?
So the parameters file is prepared manually each time?
So it's a complicated one. Let me go to the, oops. Can I show you the let me go a bit backwards. So we have this, oops, so many animations. So we have this BLUPF90. And this is a frequent source of confusion. So BLUPF90, you have a data file, a few files, and you say, BLUPF90, you are going to prepare my files for BLUPF90. And the way you do that is with one parameter file. So you say, you read this from here, and you prepare more or less in this manner. And then BLUPF90 will create another parameter file. That is the parameter file that you're going to fit in here. But the thing is that it's kind of a skeleton, so it may not be exactly what you want to do. So the way we do all the time is we copy from previous versions, basically. This thing is dying. Okay, so this is an entire parameter file. So this one, I think I copied from another one. The way we do is either we take the one from BLUPF90 and we modify, or we copy another one. Because if you are going to write everything from scratch, you will make a mistake. So for instance, you will put here 3 and then you put 4 lines, so you will forget this thing or things like that. And it depends on the order, so you cannot, it's a bit complicated. Yeah, the best is to take an example from somewhere and then modify.